Hi, everyone. Thank you for joining us in this session, Optimizing and Managing Data on Amazon S3. My name is Shovik, and I'm a product manager here in Seattle on Amazon S3. Now, when we think of optimizing storage performance and cost on S3, we tend to think in terms of four pillars. The first pillar is defining your application requirements. Understanding what your specific requirements are is key to optimizing performance and costs. For example, your application requirements drive your storage performance and your cost requirements, and you are the best person to understand what these are. The second pillar is data organization. Within an organization, we expect to see a diverse set of data sets spanning different departments and even projects. We have seen that it can really be very powerful to organize your data from the beginning if you want to effectively optimize cost and performance for your workloads. The third pillar is all about understanding your storage and how your workload behaves over time. We expect to see a wide diversity of data sets across your organization, accessed at different rates and requiring different levels of performance. The fourth pillar is what we call continuous right sizing. Now, when I say right sizing, it is really all about choosing the right storage class for all the data sets you organized and setting up the right policies that fit your application requirements. First, let's go over your application requirements. Now, the first step, as I mentioned, is to optimize and to really understand your application. And no one knows your application as well as you do. So you are the one who defines what these requirements are. And we recommend some key questions to ask yourself. What durability and redundancy do you really want? What availability is right for your use case? How often do you access your storage? What performance do you need? Do you need milliseconds latency or minutes or even hours of retrieval times? And finally, what are the size of your objects and how long you want to store them on Amazon S3? Once you define these application requirements, next you need to think about how you organize your data. You want to organize your data in a way that makes sense for the business units, applications, and users accessing these data sets. The first step to doing this is to create buckets, which are S3 resources, to upload data across different business units within an account. And to further organize your data by projects or teams within a business unit, you can use key name prefixes, which are names in front of your objects, to give a folder-like structure that help keep things organized and simple. On top of that, you can also use object tags, which are key value pairs that help you further categorize your objects across internal use cases by associating up to 10 tags with an object. Once you organize your data the right way, you can more easily apply fine-grained access controls and permissions across different departments, teams, and users. You can also apply lifecycle management rules to transition or expire data for specific prefixes or object tag-based filters, or a conjunction of both. Also, you can use object tags to monitor CloudWatch metrics by prefixes and with specific object tags to display operational metrics that are most relevant for your department, team, and users seeing a change in their application performance. We strongly recommend that you organize your data from day one to help us in the next step, which is to understand, analyze, and optimize your storage. Now, as you use Amazon S3 to manage large shared data sets across tens or even hundreds or thousands of accounts or buckets and multiple regions, it becomes more and more important to be able to access complete and up-to-date information about your storage in order to make decisions or to implement optimizations. Now, to help, S3 continues to innovate by building features that let you manage data per account, bucket, and object levels, and make changes across tens of billions of objects just with a few clicks. Our newest feature is S3 Storage Lens, as Alex just mentioned, which provides centralized organization-wide visibility into your S3 storage usage and activity, as well as recommendations to optimize your storage. We also offer S3 storage class analysis, which analyzes access patterns by different age groups to help you determine when to transition storage to less frequently accessed storage classes. And if you need to audit and report on the replication or encryption status of your objects for your business's compliance and regulatory needs, you can use S3 Inventory to get a list of all your objects and their corresponding metadata on a daily or a weekly basis for each of your S3 buckets or a shared prefix. Each of these features can help you get really smart about how we right-size our applications. Let's do a quick deep dive into S3 Storage Lens, as it was only launched a few months ago in reInvent. Storage Lens provides a large number of metrics, 29 in total, including both usage and activity. Many of these metrics are brand new and have never been surfaced on S3 console before. This leads me to my next point, which is aggregation. S3 Storage Lens provide aggregation from the highest level, which is AWS organizations, down to a very granular level of prefix. Third, metrics are updated on a daily basis. Think of it like a daily snapshot to see your storage, your usage, activity, and what you had at the end of the day. Fourth, data retention. You have up to 15 months of historical data to analyze, enabling you to analyze long-term trends and patterns, or even go back to any particular date to see a snapshot of usage and activity on that date. Fifth, S3 Storage Lens is highly visual and offers an interactive dashboard, which is embedded right within the S3 console, which can be used to slice and dice, drill down, and perform many other standard dashboard interactions on your metrics. And finally, you have recommendations, as they provide an interpretation of the metrics to help you flag outlier data points or to take action against a particular metric. Now that we have covered the pillars of knowing your application requirements, data organization, and understand and analyze and optimize your storage, we can talk about continuous right-sizing for both cost and performance in the next sections. First, let's talk about sizing storage. The best way to lower your total storage cost is by choosing the right storage class for your workloads. As you learned from the storage classes session that Alex did right before me, Amazon S3 has a number of storage classes to choose from. Whether you have demanding performance needs, data residency requirements, unknown access patterns, infrequently accessed data, or even archival needs, S3 has a storage class that is optimized for your data access, durability, and cost needs. Which brings me to our fourth pillar, which is continuous right-sizing. And the key part of this phrase is continuous. Typically, we hear from customers that their data requirements change over time, and they need to optimize for each part of the data lifecycle. And here, S3 offers two design patterns, which we see often. First, customers can use S3's building blocks with storage class analysis in combination with S3 lifecycle to move data to S3 infrequently accessed storage classes and S3's archive storage classes. In this approach, you start with the storage class analysis tool to help identify which of your data sets are less frequently accessed. Once you have identified less frequently accessed data and their patterns, you can set up S3 lifecycle policies to transition such data into a colder storage class such as S3 standard infrequent access, and then onto S3 Glacier and Glacier Deep Archive. You can also use S3 lifecycle to expire objects and their older versions based on their age. Both transitioning to a colder storage class and expiring objects and versions that you no longer need will lower your storage costs. This approach is great for predictive workloads, where objects become colder or less accessed over time. Or you can also use S3 intelligent tiering for automatic cost optimization between their different storage access tiers. S3 intelligent tiering is the only cloud storage that automatically delivers cost savings by moving objects between 4 access tiers based on changing access patterns. S3 intelligent tiering delivers millisecond latency and high throughput performance with frequent access. And now customers can choose to activate automatic data archiving to get the lowest storage costs in the cloud when data is not accessed for long periods of time. Customers can activate deep archive and archive tiers that act on objects as they get less accessed. In summary, S3 intelligent tiering can further optimize storage costs when access patterns change without any analysis, operational overload, or retrieval fees. I understand we have been talking a lot about optimizing storage costs, but what about performance? For active workloads with lots of requirements, it's crucial to think about request costs. And as you can see, there is a relationship between request costs and object sizes for a given amount of storage. So we recommend that customers batch small objects into large objects to reduce the total number of requests, then therefore their total request costs. This is particularly helpful if you have small files, such as Internet of Things use cases, with kilobyte-sized messages. In addition to reducing request costs, this is also helpful to take advantage of all of S3 storage classes. For example, some storage classes like standard infrequent access have a minimum object size of 128 kilobytes. In general, we recommend batching small objects into large objects on ingest. If you're using AWS tool like Kinesis Firehose, you can set thresholds to batch objects before ingesting them to S3. If you have existing small objects in S3, you can use services like Amazon EMR to combine small objects into larger ones. Now, I want to switch gears just a little bit here and start talking a bit more around performance optimization. One of the key things that I always start with is a view into how AWS builds its infrastructure and regions to deliver the availability, durability, resiliency, and performance you require. And we heard a lot of that in the morning sessions with the PEs. Each AWS region is made of a group of availability zones, or AZs. Each of these AZs is a standalone data center or a cluster of data centers on a single site, and they're typically only a few miles apart to isolate them from local failures like fires, floods, or power failures. And they're never more than 100 miles apart. So we can retain super high performance for S3, even when we are protecting that data by writing it across each availability zone in an AWS region. As a result of how we build our infrastructure and that Amazon S3 is a regional service, it's important to look first at the mental model of how to interact with S3, because this is different from how you should interact with some other storage services or on-premises file servers. With S3, you should think about the service as a very large distributed system accessible across a wide pool of endpoints. Within a region, you should spread your accesses widely across these endpoints, and that applies whether you are accessing a single large object from a single EC2 instance, or whether you are scanning petabytes of data in an S3 data lake from a large EMR cluster. Using parallelism across S3 endpoints lets you benefit from the scale of S3. Doing so, you can fetch data and achieve multiple gigabits or even terabits per second. So if there is one takeaway for this performance section of this presentation, is to take advantage of S3 scale by scaling horizontally for your workloads. In the next few slides, we'll discuss how you can achieve this. First, let's talk about the relationship between request size and latency. Intuitively, if you make a larger request, it's going to take longer. So the way to improve total latency is to make a number of smaller requests in parallel. For example, if you're uploading a large object to S3, you should use S3's multi-part upload and upload those parts in parallel across multiple connections. Alternatively, if you're downloading a large object, you should use byte range fetches in parallel over multiple connections. The higher level SDKs, like S3 Transfer Manager, will do this for you automatically. Now, I know previously when we talked about cost, we said you should create larger objects to reduce request costs. And then when we talked about latency, we said that you should reduce request size to reduce request latency. So what's the sweet spot and what's the right request size then? Well, it's really up to you and your application requirements. However, most customers find that the right default request size is somewhere between 8 to 16 megabytes. That's the same kind of default size that AWS CLI uses when making a multi-part upload. We've been talking about performance in the context of a single object upload and download latency. However, many applications perform activities such as MapReduce, where they access thousands or even millions of objects in a very short period of time. The same principles apply here, where you want to take advantage of S3 scale by spreading the request load across your object key namespace. Your application can achieve at least 3,500 puts and 5,500 get throughput per second per prefix in a bucket. There are no limits to the number of prefixes in a bucket. For example, if you create 10 prefixes in an Amazon S3 bucket to parallelize your reads, you could scale your load performance to 55,000 read requests per second. The key here is to spread your request load across many prefixes in the bucket. Okay, now that we have covered the fundamentals of optimizing for cost and performance, let's bring all of these practices together with a case study. We recently worked with a social media platform that is processing billions of objects and billions of events daily in their data lake, storing petabytes of data. So you can imagine the scale here. They ingested events through Amazon Kinesis data Firehose to their Amazon S3 data lake. Once in Amazon S3, they ran hourly EMR jobs to batch, transform, and store that data in a Parquet format. And then they consumed that data with tools such as Amazon Athena. Now, from the S3 point of view, first they load raw data from their Kinesis stream, transform it, and then make it available for their business analysts to query in their production data lake. They keep this data around for long periods of time as historical data. We want to take a look on how this customer optimized for both cost and performance for each of these stages. Since this customer was using Amazon Kinesis data Firehose, they were able to batch the events into larger objects, one of the best practices that we discussed before. This helped them reduce their total number of requests and reduce request costs. They also used a GUID in their key name structure. This helped create many prefixes to spread their request load across their key namespace. Finally, they set the default storage class as intelligent tiering. And as we all heard today, intelligent tiering is dynamic. For their business, they have chosen to keep their raw data around for long periods of time, and S3 intelligent tiering helped them automatically cost optimize for their raw data. Other customers that we have worked with have chosen to delete their raw data after it's been transformed, making this data short-lived. We recommend for this short-lived data, we choose S3 standard instead. Now, next we go to the production data lake. This is after the data has been transformed into optimized files, like those in Parquet or ORC formats. The files are typically anywhere between a few megabytes to hundreds of megabytes. To improve the throughput of these files, we recommend using multi-part upload and byte range fetches to parallelize across multiple connections and reduce overall latency. We also find that a lot of customers use intelligent tiering for their production data lake storage, as data in that kind of production state often has unpredictable access patterns because many business analysts are accessing the data in unpredictable ways. Finally, as the data ages, it often turns into historical data that is rarely accessed. For this customer, it was important to keep this data around to run a machine learning model training data at a later point. However, the data could offline in an archive. For historical data sets like this, we recommend using one of the S3 Glacier storage classes or opting into the new S3 Intelligent Tiering archive access tier for automatic archiving after the data is no longer being accessed. So you can use S3 lifecycle policies to move the data after a specific period of time, or use the inbuilt S3 Intelligent Tiering archive access tiers to opt into that. The choice of which S3 Glacier storage class or S3 Intelligent Tiering archive access tier that you want to take really depends on what your restore requirements are. The main difference between the Glacier and the Glacier Deep Archive, or the two intelligent tiering access tiers, is the difference in the restore experience. With the S3 Glacier storage class or the intelligent tiering archive tier, you can get your data back in as little as a few minutes using an expedited retrieval, or a few hours using a bulk retrieval. On the other hand, if you think you can wait 12 or maybe 48 hours for your data, you can use S3 Glacier Deep Archive or the S3 Intelligent Tiering Deep Archive access tier to store data at the lowest price in the cloud at about $1 per terabyte. Now, we have now walked through each stage of this data lake workflow. The key takeaway from this case study is that to achieve the highest performance and the most cost-effective storage, it's really important to optimize for each of these stages. Now, I want to put it all together and discuss what we shared today. First, it all starts with understanding what your application needs. And nobody knows your application more than you do. So start with those key questions first. Second, you should organize your data using buckets, prefixes, and S3 object tags as they map to S3 features. Analytic features like storage class analysis, monitoring features like CloudWatch, and other features such as S3 storage lengths. Third, Monitor your data by using tools like S3 Storage Lens to help you understand your data more, which can help you optimize for both performance and cost. Fourth, choose the right storage class for the most effective cost optimization. And fifth, scale horizontally to maximize performance on S3. And a bonus, finally, it's important to optimize cost and performance not on these things individually, but also for each stages of your workload. So putting this all together, I wanted to thank you so much for spending time with me today. And I wanted you to tune in for the next session for our first day of Pi Week. Thank you so much.